We are group 39 and the topic for the phase 1 is click sandwich cheating, counterfactual recommendation for mathematical clickbait issue. Our group members are me, myself, Dhruv Agarwal, Joel Joseph, and Vijender Singh Bhati.
As per the introduction of this topic, we have 5 subtopics here. First is the widespread use of recommender systems. As we know, recommender systems are essential for managing information overload across various platforms like e-commerce, digital streaming, and social networks. Second one is CTR optimization and its drawbacks. Most recommender models today are trained to optimize click-through rate, which focuses on maximizing user clicks but often prioritizes items with attractive features over quality content. So as a result, items with misleading titles or images can attract likes, leading to user dissatisfaction. This issue is widespread, making it difficult for platforms to provide high quality recommendations. So we are proposing a causal inference approach by separating the impact of exposure features, which is pre-click, from content features, which is post-click. A causal inference framework addresses the clickbait issue and improves user satisfaction in recommendation. And finally, we build a causal graph which shows different factors which affect recommendation scoring with the counterfactual approach. Can you go to the previous slide once? Okay. Which estimates the impact of exposure features. And this method is applied to the MMGCN model, which reduces the clickbait issue and improves recommendation using only the click feedback, resulting in more satisfying user experiences. As per the task for this project, we have the first one is the recommended training. And the objective of this is learn a score function S theta to predict user preference for items. We formulate this by using an equation u comma I equals to S theta of u comma I, where u represents the user features and I represent item features. Item feature includes exposure features and content features T. So for training data, we use the historical click data D bar. For loss function, the main objective of this is to minimize the loss function, example cross entropy. Inference model ranks items by UI equals to S theta bar to recommend top items. The main clickbait issue occurs when item with attractive exposure features, example for item I, are recommended over those with satisfying content, example item J, leading to the condition S theta bar is greater than for item I is greater than that of item J. So as a consequence, this results in user dissatisfaction as the user frequently clicks on appealing but disappointing items, which create a cycle of negative experiences. Such patterns can worsen recommendations by reinforcing the clickbait tendency. So, in order to mitigate this issue, we aim to break the cycle during inference by ensuring u comma I is less than u comma j, prioritizing user satisfaction over higher click-through rates. This approach focuses solely on click feedback without access to post-click feedback during training to address the clickbait issue effectively. And for evaluating this model, we focus on clicks that result in positive post-click feedbacks, not just any click. This aims to validate the effectiveness of mitigating the clickbait issue. This approach also emphasizes user satisfaction over mere click-through rates.
Moving on to counterfactual recommendation. The causal graph for existing recommender system is abstracted using the following elements: Y for prediction score, U for user features, I for item features, E for exposure features, and T for content features. These models are structured with two main components: the scoring function Fy, which predicts Y UI equals F of U and I, and feature aggregation function Fi, which derives item features from exposure and content, given by I equals function of E and T. However, this structure faces notable limitations. The current causal graph fails to accurately reflect the data generation process, leading to a mismatch. Furthermore, user behavior often skews towards items with appealing exposure features, example, clickbait, resulting in an overemphasis on these features and neglecting the content's quality. To address this, we propose a refined causal graph with a direct edge from exposure feature E to prediction feature Y to better represent the real world scenarios. The formal representation is given as f of y equals to u of ui, e of I, and e of e. In other words, when we design a recommender model that will be optimized over historical clicks through CTR objectives, its scoring function should directly take place exposure feature as one additional input. Yeah, the causal graphs of conventional counterfactual recommendation highlights key differences. The conventional graph fails to capture the direct influence of exposure features on prediction, focusing solely on indirect paths through item features. In contrast, the proposed graph includes a direct path from E to Y, enabling a more accurate representation. Additionally, the counterfactual world introduces a reference situation where exposure effects are neutralized, allowing for unbiased prediction. Figure 3 visually illustrates these distinctions, emphasizing the evolution from traditional models to counterfactual reasoning for improved recommendations. Yeah, now coming on to mitigating the clickbait issue. Even with refined causal graphs, the model still struggles with clickbait issues. This is because prediction U, Y of U, I, and E are directly influenced by exposure features, favoring items with attractive appearances over those with better content. To address this, counterfactual reasoning is introduced to mitigate the direct effect of exposure features on predictions. The counterfactual prediction is computed as YUIE minus NDE, where the non-direct effect NDE quantifies the impact of exposure. Formally, NDE is defined as difference between actual and counterfactual predictions, where NDE is given as f of y, where f of y, where f of y is function of u, I, and e, and difference of f of y with u, I star, and e, where I star is derived using reference exposure and content values. This process ensures the focus shift from exposure to content. Next slide. Now coming to objective and adjustments. The primary goal is to adjust the prediction scores by eliminating the non-direct effect NDE of exposure features, emphasizing content quality. The counterfactual scores is defined as YCR equals YUIE minus Y of UI star E. Here y of UIE represents the actual prediction and y of UI star E is the counterfactual prediction using reference exposure features. This adjustment suppresses items with high exposure appeal but poor content and boosts those with strong content but less exposure appeal. The total effect TE includes both content and exposure, but counterfactual inferences focuses solely on the content by removing NDE. This approach prevents leakage of exposure features into content and ensures a fair ranking process. Yeah, now talking about model design and training. The model design is based on two functions, which is f of y, which is function of u, I, and e for scoring, and f of I, which is function of e and t for feature aggregation. Late fusion combines prediction from conventional model u, y of ui with exposure based prediction y, ue. Using a sigmoid transformation, the final scoring function is computed as YUIE equals YUI times sigma of YUE. During training, the objective minimizes the combined loss for both real and counterfactual predictions, balancing task weights through a parameter alpha. Counterfactual inference adjusts prediction using formula YCR equals YUIE minus CU times sigma of YUE, where Cu represents the aggregation factor. This framework ensures robust training and unbiased recommendations. The main differences between these techniques are for causal graph, which accounts for direct effects of exposure, multitask training learns reals and counterfactual predictions, and CR inference subtracts ND to reduce bias from exposure features.
So in the experiment part, we analyze a model on two publicly available data sets, TikTok and Addressa. In the TikTok dataset, we have different types of features such as caption, audio, and video. The positive feedback is considered as thumbs up, favorites, or finishing a video by the user. In the dataset, we have around 19,000 users, 34,000 items, 15 lakh clicks, and 6 lakh likes. In the address dataset, which is a news dataset where titles and descriptions are treated as a exposure feature, and the news content is considered content features. A click with a dwell time greater than 30 seconds is treated as a positive feedback. In the dataset, we have 31,000 users, 5,000 items, 15 lakh clicks, and around 10 lakh likes. In the training part and the testing part, we are considering 10% likes that end with the 10% clicks that end with the likes were selected as a test set, while the rest were used for training. In the training data set, 10% of the data set was used for validation to tune hyperparameters. So this is a data set. In the graph, we can see that the x-axis represent the like and click ratio, and the y-axis represent the click and the like number. And this gray curve represent the cumulative distribution of the items. So the in the evaluation matrices, we perform evaluation by using four matrices: precision, recall, NDCG, and the rank gap. NDCG is the normalized discounted cumulative gain, which evaluates both the relevance and the ranking positions. And as we know, precision and recall, it measures the percentage of relevant items in the top K recommendations. We will choose K as 10 and as 10 and 20s. And the fourth is the rank gap. Rank gap measure the rank difference between the fake items and the real items. Its formula is also simple. Rank gap equals to rank fake minus ka rank real. So after performing our model on learning rate of 0.001 and latent feature size of 64, we get the following key matrices. In the Tector dataset, the value of P10, R10, and the N10 were respectively is 0.0269, 0.0393, and 0.0370. And the value of P20 is R20 and N20 were 0.0242, 0.0683, and 0.0476. Similarly, in the address dataset, the value of P10, R10, and 10 were 0.0532, 0.1045, and 0.078. Similarly, in the P10, the P20, and R20 and the N20 values were 0.0439, 0.1712, and 0.1133. Then we perform hypertuning on our models on the basis of the alpha values, which are tuned in the range for 0 to 5. And as we see from the graph, the best value of the NDCT score for the address and the TikTok dataset were coming at 1 and 2. So now we perform CR on two variants, CRTE variant, that is CR total effect variant, and the CR inference variant. Uh, the CRTE variant was tested to validate the importance of the purpose causal graph and the CR inference. And as we perform our model, we will see that CR inference outperformed CRTE, which confirms that reducing the direct effect of exposure feature is crucial for mitigating clickbait issues. And as if we see in the results that CR inference values is more than CR total effect variant values in both the data set. when we perform the in-depth analysis of our models, we find it out that that in the CR that the CR model recommended fewer atoms with the like click ratios less than 0.6 and more atoms with the like click ratio more than 0.8, which tell us that CR is better at avoiding clickbait and recommended items that are more likely to satisfy users. And second, if we the effect of dataset cleanliness, we obtained that if we clean our data, that is decrease more like ending with dislikes, then the CR consistently outperform the performance gap. Now we see the effect of the fusion strategies. As we know, any differentiable arithmetic binary operations can be equipped as the fusion strategy in the CRs. uh, there are different fusion strategies we follows. Uh, the two of one of them are MUL and the SUM strategies, which are trained on different activation functions. That is linear, sigmoid, and 10H. These are the different formula for the different activation function for SUM and MUL. And as the performer model, we find it out that the non-linear fusion strategies generally outperformed linear ones, achieving a better performance across both data sets. Now, if we evaluate CR model on the synthetic data, for the synthetic data experiment, we we created created some fake atoms by poisoning the specific features. The evaluations aim to assess how well the model could differentiate between fake and the real atom based on the rankings. And we will see that in CR, a large rank gap indicates that the model effectively suppress the influence of clickbait items while promoting genuine content. The CR is effective in like increasing the rank gap and giving us better results.
Okay, so the clickbait issue is prevalent in industrial recommender systems, and to address it, we proposed a new recommendation framework, CR, which is counterfactual recommendation, which incorporates the causal relationships among exposure features, content features, and predictions. By utilizing counterfactual inference, we estimated and removed the direct effect of exposed features on prediction scoring. While counterfactual recommendation was instantiated on the MM's GCN model, it is model agnostic and requires only minor adjustments to be adapted for other models, enabling broad application across various recommendation scenarios. Mitigating the clickbait issue enhances user satisfaction and engagement, paving the way for improved recommendation quality. This research opens a new direction, incorporating counterfactual inference into recommender systems, encouraging future exploration of constructing more comprehensive causal graphs, investigating other intrinsic biases in click data such as selection and position bias, emphasizing the importance of causal inference techniques like intervention and counterfactual inference in empowering recommender systems.